Okay, so this is going to be section 3.2, polynomials, polynomial functions specifically in their graphs. So we're going to take a look at what a polynomial is. We're going to define it first, and then we're going to look at some of the key features that are going to help us to figure out how the graphs work. Alright, so the first thing is let's define a polynomial. A polynomial by definition means that the function itself, all of the exponents are whole number exponents. So all exponents are whole numbers. Meaning you could have an exponent of 0, 1, 2, and so on. But you can't have anything in between. You cannot have a fractional exponent. You cannot have a negative exponent. All the exponents on the variables are whole number exponents. And you're also going to have coefficients of the variables. And the coefficients of the variables are simply the numbers that get multiplied times the variable. For example, a polynomial function might look like this. Negative 3x to the fifth plus square root of 2 times x squared plus 5. This is a polynomial. And the reason that I know that it's a polynomial is because the exponents themselves are the 5 and the 2. Those are whole number exponents. Excuse me. The coefficients, so in green here, we're going to say those are the exponents. The coefficients here in blue are the numbers which are getting multiplied times the variables. So in this case, our coefficients are negative 3 and the square root of 2, both of which are perfectly fine because they are just numbers that are sitting out in front of the variables. Technically, this 5 out here is also a coefficient, but there's really no variable that it's being multiplied by. That's because it's technically x to the 0, but we don't write x to the 0 because that's actually just 1, so that's not something is written there. But technically 5 is also a coefficient, but more than likely we're just going to call that the constant because there really is no variable that's being multiplied times. That's the constant. Okay, so the reason that I'm giving you these definitions of things is because in order for us to be able to figure out how these polynomial functions are going to behave graphically, we need to be able to know the definitions of coefficients and exponents, because we're going to have to be able to talk about the degree. So let's do, in red here, we're going to have to talk about the degree of a function, of a polynomial function. And the degree is the highest exponent. So if you look at the example that I wrote down here, the degree of this polynomial function is going to be 5 because it is the biggest or the largest exponent. And you have to be careful because I wrote this in descending order, meaning that the largest exponent was first and then the smaller exponents come after that. Not always going to be the case. You just have to be careful to look for that. You look for the highest exponent. That is going to be the degree of the function. So this one specifically has a degree of 5. And the leading coefficient is the coefficient that is attached to the highest degree term. In this case, the leading coefficient is negative 3 because it is attached to the highest degree term. So leading coefficient coefficient is the coefficient multiplied or attached to the highest degree term. Alright, so that's just kind of a good start there for us. And all polynomial functions, when it comes to their graphs, are going to be what's called smooth and continuous. So let me demonstrate. The graph of a polynomial is smooth and continuous. Okay, so the smooth part just means that if I was to graph it, it's going to have no corners, no rough edges, so it would look something like this. So you can see how when this graph turns, so it turns and changes direction right there, it changes direction there, there, and there. It's got 4 different places where it changes direction. All those places are smooth. Okay, there's no corners, there's no sharp edges. Just to show you what one would look like that's not smooth, maybe something like this would be a graph that, would be a graph that isn't smooth. So you can see right there, at that place right there, that's not a smooth edge. That's more of a sharp corner. We actually call that a cusp. It's not necessary that you know that, but you can definitely see the difference between something which is a smooth edge and which is not a smooth change of direction, So the one that I have over here in blue, and we'll just call that one number 1. And this one over here, number 2. Number 1 is smooth, and it's also continuous. Now, one thing I didn't show you was with something that's discontinuous. And discontinuous means, and we'll call this one number 3, discontinuous means that it actually has a break in the graph somewhere. So here, let's try a different color. Let's go with something like purple or something. Let's try that and see. So discontinuous means that it might do something like this. It is smooth up until here, and then all of a sudden, now it picks up back up here and does something like that. So that right there would be discontinuous. As you can see, there is a major gap in the graph between here and here. There's a gap. That is not continuous. So this would be not continuous. And therefore, that cannot be a graph of a polynomial function. And this one right here is not smooth. Therefore, that cannot be a polynomial function. Only number 1 here is polynomial. So number 1 is polynomial. The other 2 are not. So again, that's kind of what we're looking at when we're talking about the graphs of polynomial functions. It must be smooth and it must be continuous. And the graphs that we are going to be creating will be. Alright, so there's a couple of things that we need to look at in order for us to be able to tell what the graph is doing. The first one is called end behavior. End behavior. Basically, that is what is happening at the ends of our graph. What's happening as the graph goes way to the left, what's happening as the graph goes way to the right. Everything in between we'll be able to figure out using some other criteria. But the end behavior is not really that difficult to do. You're going to look at 2 things. We're going to look at the leading exponent, or the highest degree. So we're first going to take a look at the degree of the function. And then we're going to look at the leading coefficient. So it's kind of a degree and a leading coefficient test. So the first thing we're going to talk about is if the degree is an even or an odd value. So we can have 2 possibilities. The degree can be odd, or the degree can be even, meaning that if I have something like 3x cubed plus 2x plus 5 or something like that. The x cubed is the highest degree. Cube, or to the third power, is an odd value, so that would go in that category. If I have something like 5x to the fourth, x to the fourth being your highest power, would mean that it's even. So first of all, let's look at one that is odd. If the highest degree, or if the degree of the function is odd, then what you're going to do is, first of all, odd means opposite, and that's kind of the way I always remembered it. The fact that O and O, odd and opposite, means that the ends are going to go in opposite directions. So let me sketch what I mean by that. You're going to have two possibilities. So I could have a situation where maybe whatever I have starts down, like it goes this direction, and then it comes up and does something, whatever it does, it turns however many times it turns, but then it finishes up. Okay, so that's a possibility. It could start down at the left and then finish up on the right. Or, just the opposite of that, it could start up and then it can change however many times it's going to change, and then it could finish down. And the way you're going to be able to tell that is from the leading coefficient. So the leading coefficient here is going to tell us which way this goes. So if something starts down and finishes up, you can kind of see the general trend over here on number 1, that it starts down but it finishes up. So the general trend from left to right is positive. It's going from a low value to a higher value when it finishes. Well, that's because the A value, or your leading coefficient, is positive. So your leading coefficient here is positive. For number 2, again, now what you can see on number 2 is that it starts higher and then it finishes lower from left to right. And again, we always read graphs from left to right. So it starts high and then finishes low. That's because the leading coefficient would be negative. So let me just kind of write an example of what this could look like. These are not going to be exact, but it could be that maybe on the first one, f of x is something like, I don't know, it's got to be an odd exponent, so like 3x to the 7th minus 2x squared plus 1 or something like that. So you can see that the exponent is a 7, so it's odd. The leading coefficient is positive 3, so it's going to finish up. So it starts down and finishes up. On something like number 2, still has to be an odd exponent, and that is a cubic of some kind. So it might be like an x cubed minus 2x squared plus 3, something like that. But it's got to have a negative coefficient, so maybe it's like negative 2 out in front, because it's got to start up and then finish down. So in this case, the coefficient was negative, so it goes down. Here the coefficient is positive, it goes up. And the exponents, the highest or leading exponent, highest degree, is odd. Then we can have the possibility where you have an even degree. And for an even degree, unfortunately the E does not go with what I'm going to write here. These are going to finish in the same direction. The ends will go in the same direction. So again, there's two possibilities here. So we'll call this one here number 3. And we'll call this one over here number 4. So you could have a situation where the graph starts up and does whatever it's going to do in between and then finishes up, same direction. Likewise, you could also have one that starts down and then does whatever it does in between, however many times it turns, and then finishes down. So as you can see, the ends on either side, left and right, go in the same direction. The first one, they both go up, and the second one, they both go down. So again, you're going to look at your leading coefficient, and hopefully it makes sense. If both things finish up, it's because you had a positive leading coefficient. If both things finish down, because down is a negative direction, it's a negative leading coefficient. So again, just to give you kind of an example here, the first one might be f of x equals, because it's positive, so maybe like 3x to the fourth minus 2x plus 1, something like that. The second one here, because it's negative, might be f of x equals negative 3x to the sixth plus 4x minus 3, something like that. And I'm just making these things up. But again, what I really want you to focus in on here is that this one had a positive leading coefficient and an even fourth power exponent. This one had a negative coefficient, which is why it finishes down and down, and an even exponent. So those are how you're going to determine end behavior, looking at both the power, the highest degree, and the leading coefficient. That'll tell you what you need to know.